I guess none of us are total strangers to this algorithm, divide and conquer. We have seen it many times in the fundamental course, right? So today we're gonna get a closer look at this algorithm. We'll check more examples and study different methods of analyzing the complexities with recursions. Say divide and conquer is usually implemented by recursions. Recursively, we first divide the problem into a number of subproblems and then conquer them. Conquer the subproblems by solving them recursively. And finally, we're going to combine the solutions to the subproblems into the final solution for the original problem, right? When we analyze the time complexity, usually we have this kind of recurrence equation. So eventually, the original problem of size n will be divided into several different parts of each of the sides n over b. And finally, we have to combine the solutions. It takes that many time to combine the solutions. Okay, plus the time taken to recursively solve each of the subproblems. Altogether forms T of n. So in the fundamental course, we have encountered this algorithm several times. Do you still remember? Like at the very beginning of the course, we discussed 4 different solutions to the maximum subsequent sum problem, right? And the third one is the divide and conquer algorithm, runs in n log n time. But keep in mind that n log n is not the only possible complexity function we may have. And another example is the tree traversals. It's also an application of divide and conquer. So basically, we divide the tree into several parts. The root plus its subtrees, right? And we recursively conquer its subtrees and combine the results of the root. But the time complexity is not n log n, but it's linear. It's just big O of n. And others like merge sort and quick sort are both n log n. And later on, we're going to see that with divide and conquer, we may obtain all kinds of complexities with some strange functions, like big O of n to the power of 1 point something, 1.65, things like that. All right, now let's take a look at our first example for today, the closest points problem. The problem is, given n points in a plane, we're supposed to find the closest pair of points. And if 2 points have the same position, then that pair is the closest with distance 0. So this is the trivial case. And later on, we're going to assume that all those points are placed at distinct positions. All right? And the simplest solution is a simple exhaustive search, which means we can just check out all the pairs of points and calculate their distances, and therefore to find the closest pair with the smallest distance. Okay, that's exhaustive search. Then how many different pairs should we check? It's n times n minus 1 over 2, right? And therefore the time complexity would be big O of n squared. Okay, and remember what I've said in the fundamental course. Being professional means that whenever we see an algorithm runs in n squared time, instinctively we should try to reduce it to n log n, right? And if we can do so, it will be a big improvement since n log n is much faster than n squared. So here comes the idea of divide and conquer. And actually, the idea is very much similar to the maximum subsequent sum problem. So what did we do with this problem? Step 1, divide it into 2 parts, right? So for example, if we have that many points in the plane, step 1 is to sort them according to their x coordinates and divide it into two parts. So sort according to x coordinates and divide. And then what? Conquer, right? Recursively conquer the left-hand side and obtain a shortest distance, and recursively solve for the right-hand side. Plus, we must find the closest pair cross the border. It's just similar to the maximum subsequent sum problem, right? So the final solution must be one of these three answers. Sounds quite simple. So we conquer by forming a solution from left, right, and cross. So it's so simple, and we clearly have an n log n algorithm. Well, say the conclusion is that we do have an n log n algorithm, alright, but is it really clearly so? If we are not careful, we're not gonna get this n log n. Okay, if we are not careful, we'll probably end up at n squared. Let's see why. So just like finding the maximum subsequent sum, we have a equals b equals 2. That means we divide the problem into two parts, roughly equal sized, and then just sum them up. And how about that combined part? How about that f of n? F of n is the time taken to find the cross distance. Okay? So the key is whether or not we can find the cross distance in linear time. Let's see. In the fundamental course, when we analyze the maximum subsequence problem, we have an equation like this, right? It takes t of half of n time to recursively solve for the left-hand side and right-hand side, add them up, plus it takes only a linear time to find the answer cross the border, right? And if we have this equation, then every time we can replace n from both sides by half of n, and we obtain a function of t of half of n, and plug that expression back into the right-hand side, we obtain this one. And simplify it, we have 2 squared times t of a quarter of n plus 2 times the constant times n. And we can keep moving like this, right? Replace n by a quarter of n from both sides and obtain an expression of t of quarter of n and plug it in. And then eventually we're going to end up like n plus some constant times n log n. And we take the larger term and therefore obtain big O of n log n. That's when we have a linear function here to combine the solutions. What if this part is not n but n squared? What do we get? Okay, I suggest you to pause the video here and try to derive the answer by yourselves. So here we go. Every time we are having an n squared, not an n here. So eventually we're going to get this part is n, this part is 1, and this is n squared times some constant number. Okay, so this is going to be big O of n squared, not n log n. So this term is the key to the final conclusion, right? So we can obtain n log n only if we can find the cross solution in linear time. But can we really do that? Okay, think about it. How are you supposed to find the cross one? If we have to do, say, for every point on the left-hand side, we calculate the distance to every other points on the right-hand side, it's going to be n squared, right? And therefore, we are going to obtain big O of n squared as the final conclusion. That will not work. So the point is we should try everything to reduce the time complexity of finding this solution. The first thing we can do is, instead of considering every point, we simply consider the points sitting in this delta strip, where this delta is what? Delta is the smaller distance between these two distances. Okay, take the smaller one to be the delta, and we only consider the points sitting in this delta strip. And see, if the number of points in the strip is big O of square root of n, if there are only square root of n points in this delta strip, then we do the nested for loop to check all the pairs. These numbers are just square root of n, so put them all together, it's going to be n instead of n squared. And hopefully it can work. But if unfortunately everybody sits in this delta strip, then this number is no longer square root of n, it's big O of n, and still we get n squared here. So it doesn't work in the worst case. So what else can we do? Well, so besides having this vertical delta strip, let's also consider the horizontal one. Let's add a horizontal delta strip. So it's a delta square. Let's only consider the points sitting into these two delta squares, and we check the points from top down, one by one. Okay, and therefore we have this nested for loop, and we say that the total complexity is big O of n. Why? Because the worst case is like this. In the worst case, we only have to consider at most 7 other points. One of the points must be that piece of I itself. Okay, and at most there are altogether 8 points sitting all at the corners. Why? Why is it impossible to have any point inside? Because this length is already the smallest distance, right? It's impossible to have another point inside which can get a smaller distance. So that's impossible. So in the worst case, there are never more than 8 points sitting at the corners. And if one point is P sub I, and we only need to check at most 7 other points, and 7 is a constant, and therefore it's a constant times n for each P sub I. So even if all the points are sitting into this delta strip, still we can get a linear function to check every one of them. And if this is linear, then finally we can obtain n log n as the result.